Hey everyone, welcome back. So far in this chapter about radicals, we have learned how to simplify perfect radicals where they come out exactly as a number, such as like the square root of 25, it's just 5, or the square root of x squared, it's just x. And then we also learned how to simplify non-perfect radicals where you end up with a square root still in your answer or a cube root still in your answer. You don't have a perfect number of pairs to pull out as factors. So we've learned all about simplifying. Next, we're going to learn about multiplying radical expressions. So I kind of added in a little bit of typed notes on here that you might want to either write or type in. When you're multiplying radical expressions, there's 3 steps that you have to do. Step 1, multiply the numbers outside together and leave them outside. Step 2, multiply the radicands together and leave that product under the root. Just so you know, radicand just means the number under the root. And finally, you always want to see if that new radicand can simplify. So I'm going to give you like one problem where we're going to go through all 3 of those steps and then also show you how to do it a little bit easier instead of multiplying them all the way up, because you'll end up having to probably break them back down anyways. So let's take a look at this example, square root 2 times square root 14. These don't have any numbers on the outside. Technically, that would be a 1 square root 2 and a 1 square root 14. But you don't need to worry about that because 1 times 1 is still just going to be 1. So just look at the radicands. You have 2 and you have 14. Since they're both under a radical, the product stays under the radical. 2 times 14 makes 28. But then you have to check, does 28 have any perfect squares in it? Let's find out by making a factor tree. I know that the factors of 28 include 4 and 27, and 4 is a perfect square of 2 times 2. What we learned yesterday is that we can simplify square root 28 and make it break down to square root 2 squared and square root 7. By breaking it down to 2 squared and 7 instead of 28, I can cancel out the square root with this perfect square, and I end up with just 2 square root of 7. That's my final answer. If you wanted to, what you could do before you multiply them together is break them down. 2 is already a prime number, but 14, I know that can break down into 2 and 7. I immediately see my 2 times 2 and my 7 by itself. So you could skip straight to the step where you go 2 squared, square root 7, instead of making it a 28 first. Making it a 28 is actually kind of just doing extra work because you end up breaking it back down into smaller numbers anyways. Let me give you another example where we have numbers in the front this time. So you're going to multiply the numbers together that are out front. 3 times 2 to get you 6. And like I said, you could multiply together the 2 and the 6, but then you're going to have to probably end up breaking it back down. So go ahead and look at your 2 numbers. 2 is already prime, but 6 can break down into the factors of 2 and 3. I noticed that I have a pair of 2's here and my leftover 3. So what I'm going to do is I'm going to write this as 2 squared and 3 under my root. Remember, a squared and a square root cancel each other out. So I end up with 6 times 2 times radical 3. There's nothing to cancel out the radical over the 3. So the 3, since it doesn't have a matching factor, it's not a perfect square. It has to stay under the radical. Now to get my final answer, I'm going to multiply the 6 and 2 together to make 12 and bring down my radical 3. Alright, now I want you to try a couple of these on your own, so go ahead and pause this video and see if you can simplify each expression. Here are the final answers for the first two, where there weren't numbers in the front. And then here are the final answers for the second two, where we do have numbers in the front. We're going to try a couple more extra examples that weren't in your book, but I think it's important for you to see this. Like I said before, if there's not a number in front of the radical, you can assume that it's a 1. So in this case, you're taking 1 times 2, you get 2, and then you look at your radicands, 6 and 3. But before you multiply that up to 18, I'm going to check if I have any matching factors. I know 6 can break down into 2 and 3. 3 is already a prime number, but I notice I have a pair of factors now. So instead of making that an 18, I'm going to make it 3 squared and 2. That way I can cancel out a squared and a square root, but the 2 has to stay under the radical because it's not a perfect square. Only perfect squares can come out. So I end up with 2 times 3 square root 2. And then the last step is just to multiply this 2 and 3 together to get 6 and bring down your square root 2. So your final answer is 6 square root 2. Let's do one more together with some variables thrown in here now. So let's look at the numbers in the front. We have 4, and technically this would be a negative 1. So 4 times negative 1, I know that's going to be negative 4. And now let's look at my numbers under the radical. I have 28 and 7. Rather than sitting here and multiplying up 28 and 7, I'm going to break down my 28 into 7 times 4. I see a pair of 7s, but I know my 4 can break down even further. That's not a prime number. 4 can go down to 2 times 2, so I actually have another perfect square, 2 times 2. Okay, now let's look at our x's. I have x and I have x cubed. Well, first, let's go ahead and finish my numbers here. I have 7 and 7. So I have 7 squared under my radical. And I have 2 and 2, so that's a 2 squared. And remember, since it started out under the radical, it has to be under the radical until the perfect square cancels that out. What I would suggest for the variables is to go ahead and multiply them together. So my x's, I have x times x cubed. Remember the property of exponents tells us we add exponents here when you're multiplying. So x to the first times x cubed gives you x to the fourth. And then y cubed times y cubed gives you y to the sixth. I'm going to go ahead and just put those in separate radicals. You could put them in the same one. That's not really a big deal. All right, bring down my negative 4, bring down my 7, bring down my 2. Now let's inspect these variables. So 4x to the fourth, I know that I could split that up to be x squared and x squared. There's 2 groups, perfect squares here. With y to the sixth, I know I could make that y squared, y squared, y squared, and that would make y to the sixth. There wouldn't be anything left over. Now go ahead and cancel out any perfect squares with its square root. And actually what happens on this problem is that all my square roots are all canceled out. So I end up with negative 4 times 7 times 2 times x times y times y times y. Now I just multiply these back together. Negative 4 times 7 is negative 28. And then 28 times 2, that's going to be negative 56. X times x is going to be x squared. Y times y times y is going to be y cubed. Remember yesterday we talked about the shortcut is you can say, okay, with x to the 4th under a square root, how many groups of 2 can you make? How many groups of 2 can you make? You can make 2 groups of 2. So that's why in your answer it ends up as x squared. And there's no x's under a radical because there's nothing left over. Similarly, for y to the 6th, how many groups of 2 can you make? You can make 3 groups of 2. That's why it's y cubed in the answer. And there's nothing left over, so that's why there's nothing under the radical. Go ahead and try this extra practice problem here. This is going to be the last one that we finish with today. Here's the correct answer for that. And then in the next lesson, we're going to learn about how to divide radicals. So I look forward to talking to you then. See you soon. Bye.